I'm going to show you something that is related to another talk. It gives you an idea of how mathematics can be presented in a different way. I call this cognitive impression integrals. You familiar with this one? Yeah. Archimboldo. This one is in Gripsholm's castle. This one is in Skokloster. So it's this one actually. And Sara sitting over there, you're working with this kind of stuff, right? So I mean, Archimboldo was a fantastic before his time. It's almost like in his own universe back in the 1500s. And he does this, what I call, this is Archimboldo's impression integral. What does he do? He takes all the parts, all the fruits, and integrates them. They're all non-facial parts. They don't belong in faces. He integrates them into a facial gestalt, into a facial whole. So he takes the impossible parts and sums them up into a possible whole. And this he does by moving in this, going from the impossible to the possible is done by defocusing and focusing attention. It's done by looking at the whole, looking at the detail. Moving in and out, almost like you're zooming in and out. So the abstract integral type here is integrating over all the parts, impossible parts become possible whole. Now we look at the opposite of that. This is Oskar Reuterswärd as an 18-year-old high school student in 1934. First impossible figure that we know of. And he was criticized by his teacher because it wasn't correct. He got no appreciation for this. So he calls it, well, there's some links in this also. If you're interested in this kind of stuff, you can go exploring. So here I call this, Reuterswärd sets these cognitive trap cycles. Because in an impossible figure, you start out walking along a certain path mentally, and you come back and you have a different conception of space than the one that you started out with. That's if you look back at this. You see you're moving here horizontally, and then you're moving one step down. Then you're moving horizontally again, but you're back to where you started. How can that be? You went down one step. So you should be down one step. No, but it doesn't fit. That's a cognitive trap cycle. So Reuterswärd does this. He sets these cognitive trap cycles by inviting people to take closed walks within his spaces. That's what you do. I mean, we are prone to do such things. And if you walk small enough, then it's okay, just around a single corner or something. But in the walks that are implicitly promoted by the structure of the image, the experiencer will often fail to produce a coherent impression, because you will come back with a different impression than the one which you left. So Reuterswärd does the opposite of Archimboldo. He takes possible parts and integrates them to an impossible figure, an impossible whole. So the abstract integral type, sum of all possible parts are impossible whole. In fact, mathematically, the impossibility has to do with the impossibility of embedding this thing in three-dimensional Euclidean space. So it's not really impossible, it's just non-embeddable. But that's a mathematical sharpening of this that takes some explanation. So integral of embeddable parts may become non-embeddable, and that's the abstract manifold concept, which is lurking in Reuterswärd's art. And I haven't seen anybody really pointing that out seriously. So there's a cognitive duality between Reuterswärd and Archimboldo, as expressed here, these abstract types. So if you look at them as operators like we love to do in mathematics, Reuterswärd is an operator that goes from the locally possible to the globally impossible, whereas Archimboldo is an operator that goes from the locally impossible to the globally possible. So this is an example of what we mathematicians do. We look for patterns like this, patterns that try to capture things so that we don't have to remember them too much. At least sometimes. That's why mathematics is described sometimes as the lazy man's guide to enlightenment. And unfortunately, man, most mathematicians through history have actually started out as priests, in priest careers, being trained at university as theologians. And then, just like people come out as queers or whatever today, they came out as mathematicians, much to the pain of their supporting families who didn't see how they could have a secure career. And they couldn't, of course. Great mathematicians were astrologers and were fed with very unsecure positions because there was no subject called mathematics really at that time. So that's showed you some examples here of what mathematics is, meeting mathematical structure. In fact, I think I will finish by showing you one more, which will give you an idea of what the richness that mathematics has, if you look at it from a good way. This is called the Penrose triangle, and Penrose and Penrose didn't know about Reuterswärds work when they introduced this in British Journal of Psychology in 1958. Here is some work on fooling the eye a bit. Impossible doubts. I don't know where I found this on the web. I don't know. There was no reference. If anybody knows that, please send me a note. And basically, the cognitive trap cycle is the fact that you are going here, starting, you're moving horizontally, moving one step down, just like the Reuterswärds thing, and you come back to the same place. So start plus floor plus down equals start. And there's one down too many here for things to come together in a nice way. Reuterswärd created this very nice around 1952. I'm not exactly sure about the date there. But if you start looking at this, you see that it has a strange mixture of possibility and impossibility. Here is if you put our little mental walker in here, walking horizontally, down one, down two, and so here is two down. It's two down when you did this. Strange cognitive distortion. Now here's Escher, 10 years later, utilizing exactly this. Escher was inspired by Reuterswärd. He didn't invent these impossible figures himself, he just used them. And here you can see also how he slants the bricks here so it looks like the water is running down all the time. So he makes even this floor thing a little down, a little down, a little down, a little down, and much down. So that's the waterfall, a famous picture by Escher. Now in mathematics, there's something called homotopy calculus. And I'll explain to you what that is. You know, in the old Norse mythology, there's this Midgård, that's basically the world. And then there's this snake, the Midgård snake, that crawls around the world and bites its own tail. And the question is, mathematically speaking, in how many different ways can the snake do that? How many different ways can a snake crawl around the world and bite its own tail? And what do we mean by different ways? And there are different ways of measuring that difference, but one way, natural way of measuring that difference is called homotopy. So here we see these two snakes crawling around the world of a torus. Sorry, I'll pull that back to there. Here you can see the results. The snakes have bit their own tail. And if I will play you that in a movie. This is a tool, a wonderful tool called the graphing calculator, by the way. And then I've spliced that up with another movie that shows basically, sorry, we'll make it larger here. Sorry, here you see the homotopy. Here you see, this is called a homotopy. It's a continuous way of transforming one snake into the other. The snakes were made of rubber, like rubber bands. You just smoothly move one into the other. So these two snakes are homotopic. So this is the same way of crawling around, even though it looks a bit different, but it's not. So we are saying that two snake crawls are equivalent or the same if one can be moved into the other like that. That's called homotopic, and that's called a homotopic calculus. It turns out that what we're interested in is the torus here. If this had been a sphere, if this had been just a ball with no holes in it, then anyway the snake had crawled around and bit itself would be the same, because they can all be, then it's easy to see that. That's just one single way of doing that. It's a trivial homotopic group, as you say in mathematics. But the question is here. If you think a little bit about it, you will find that it's basically the number turns around the ring and the number turns around this way. If you do the same number turns longitudinally and latitudinally, then you get homotopic snakes. And we say in mathematics that the homotopic group is the set of pair of integers. One integer telling you how many laps this way, and then there's positive direction this way, -2 laps is going 2 laps this way, and +2 is so on, right? You can make, and what you can see then, this is homotopic calculus. And when I talk about the homotopic calculus for impossible worlds, then these homotopies are, in fact, just as it's in fact, two distortions are the same if their difference is possible. If the one can be transformed into the other with a non-cognitive, you will see, best to see an example. Here is a blue, this is a 1 down thing. And this going the other way is a 1 up. So notice that this is impossible, this is impossible, but the sum, if you sum these up, what's going to happen then is that these two arrows will cancel each other. So you sum them up, you get these 4. You go 1 step horizontally, 1 floor up, 1 step horizontally, and 1 floor down. And then you have a possible trip. So the sum of these two impossibilities is possible. So you have the same thing here. 2 down, 2 up. So there's a calculus, basically, just like the snakes were homotopic when you could move one into the other. These paths can be moved into other paths without any impossible difference. If the difference is possible, then the paths are homotopic. And it's just another realization of the same idea. This is the kind of thing that excites mathematicians. You see patterns appearing in places where you didn't expect it. That's what mathematics is about. Stefan Banach, a great mathematician, said, good mathematicians see analogies. Great mathematicians see analogies between analogies. So, with these words, I'll close this little attempt to describe what mathematics is really like. If you work with it, why you would like to work with it, how can you waste your life on it? Well, because of stuff like this. Because you get to experience things that art can take you halfway, but not fully there. In the 1400s, when perspective was developed, the artists were the mathematicians. And I think we can get back there. I think that there are a lot of connections. Gudrun Sandvik in Malmö Högskola, as an art professor, described mathematicians in a way I think it was in the Filosofiska rummet a month or two ago. The best thing I ever heard said about mathematicians by an art professor, and that made me happy. So there's hope for the future. Okay, thanks guys.